extensionality. A set is uniquely determined by its members. The empty set exists. You can do this weird unordered pairs thing where you make a new set out of, given two sets, you can make a new set such that those two sets are members. You can take the union of a set, which is you dump out all the candy inside all the bags inside your big bag. Does anyone remember from yesterday? Good. And you can do so-called subset construction, which means given a set, you can construct all the subsets that have some certain property. Okay, so we were, in order to, this is quite technical, and in order to master this task, I have set before you to construct these 4 sets. So go.
We already did
started this at the end of class. Maybe if you were very smart, you just did it in 5 seconds. I started doing it over here.
We already did it.
You already did all 4 of these?
Not all 4, we did the first 2, and
down.
then after that it's like...
No, it gets hard again.
Oh, really?
It's the same thing.
Oh,
The fourth one.
oh no, the 4th one's like whack.
The fourth one.
They're all hard.
I mean, the first 3 are straightforward.
So, would you like to see what I did already on the board?
We have that one. The first 3 are just we have it.
No, it's not as easy as it seems. I guarantee you this is one significant level harder than it appears at first. That's a strange guarantee, but this is... wait, can you guys not do that thing where you just kind of sit there, just kind of... Come on, get a piece of paper, get a pencil, get active, get engaged, get hunched over, moving, talking, you know, like...
Wait, yeah, we just keep on doing it. Then we have.
It's a little hard though.
We take anyone and then we pairing.
Yeah.
And then we end up with 2, and then we union it. That's we're unordered pair again. With that and then we do some union. Yeah.
Yeah. So we have good. Yeah, we have so
Good work, Sam.
Okay, good. So yeah, we have the empty set. The empty set is a set. So just like fact, notice how my convention here is I'm putting a colored box around a set once I have constructed it. Okay, can you accept that convention? Say yes.
Yes.
Good. Now I said this at the end of class yesterday. Many of you spontaneously figured this out. I think Adam even mentioned it during the body of the presentation yesterday. But the unordered paired axiom, I explained it as given 2 sets, x and y, you can make a new set such that those 2 sets are members. Precisely those 2 sets are members. But, as I think I mentioned, you can set x and y to be the same set. That's what's going on here. I personally find this kind of tricky and not obvious. If I apply the unordered pairs axiom, the axiom which was advertised as an axiom which can take 2 sets and make a new set such that those 2 sets are members, if you apply it to the empty set and the empty set, after all, it's the only set we have at this moment, then you get the set with quote-unquote 2 members. But in fact, they are the same member, and the justification that this set is the same as this set, if you want to be very serious about this, is that Axiom 1 says that 2 sets are the same if they have the same members. Who is with me? Good. So bullet point number 1, done. I constructed the set containing the empty set, which is after all an important number because it's like the number 1, right? Okay, how about the second bullet point? Well, that's also easy to make the set containing the set and the set containing the empty set, which is after all the number 2, right? How do I do it? I simply apply the unordered pairs axiom to the only 2 sets I have at the moment, and then I just get it right away. Okay, but how do I make this next one, which is, by the way, not the number 3, right? It's actually just some weird new thing.
Construction.
Oh. If you're gonna play with it, can you do it somewhere else? I got precious seconds left in this semester. I gotta just go hard every second.
Hi, Mr. Shaver.
Such demoralization.
Dang, he was all excited too.
It'll be here all year.
How do we make the set of the set?
Yeah, this I
you
think
can
this
just
is hard.
You can just like
Oh,
make
you
a
just-
set of a set with
You
a
just
bunch of
pairs.
pairs. You keep on like unordered pairing things together until you end
You just
up.
unordered pairs.
Yeah, you unordered pair two of those, and then you get a
Alright,
set.
Sam has proven me wrong by, in fact, demonstrating that he really did get it, like,
You
instantly.
can like effectively just like make
Yes,
any number of sets.
yes, Sam is saying that effectively, the unordered pair axiom, whenever you apply the unordered paired axiom to the same thing, you effectively get to wrap that entire set in another pair of brackets, yeah?
Any set.
And so, if you, in step 4, if you apply the unordered pairs axiom to, what should we apply it to?
The red box number 2.
Yeah, the set containing the empty set and the set containing the empty set. Then what does that give you? It gives you the set containing the set containing the empty set and the set containing the empty set. Which is, because a set is uniquely determined by its members, just the set containing the empty set. Everyone, who's good? Okay, I'll put a purple box around that. But now what should we do?
You beat that one with.
You need to do it again. You need another set.
Yeah,
So
do you
that
see
one
this
you need-
third bullet point? This third bullet point is a big bag with 3 things in it. But before, yeah, Sam gets it. In order, you're not ready yet, right? Because this is what you want, this set you want to be in your final big bag of Halloween candy. So you first need to like wrap it again. Anyone know what the hell I'm talking about? Or does everyone? Maybe everyone knows what I'm Okay, good. So contrary to, it's not immediately obvious, at least to me it isn't, that this is necessary. But yeah, you need to do this entire move one more time. Because this purple set needs yet another wrapper on it, so that when I build a big set and then union them all together, then I'm going to get this third one. Alright, we'll just find out if anyone's with me or not. So we're going to apply the unordered paired axiom now to that thing, and that thing. Why would I do such a crazy thing? Because then I get a new set. Cha-cha-cha-cha. Oh, ZFC. Frame also. And then that gives me zoom zoom. Is that really, is all this really necessary? Yes. Now what do I do with the set that I constructed in step 5? Can someone see if I'm in frame?
No, you're fine. Okay, maybe not.
Oh, like the whole board is in frame, so like if you're like,
Now what? Yeah, Adam.
The board is still row 5 up to where it
Yeah, now wait, say it again? 3 and 5, right? No, first unordered pair 3 and 5, is that what you said?
Yeah.
I think that's the only path. The union of the unordered pair. Yeah, I'm doing it step by step, but yes, you are right. And so now, you unorder pair together, apply the unordered paired axiom to the set in step 3 and the set in step 5. So the set in step, this set, cha-cha-cha-cha, and this set. Which yields a new giant set, which has precisely 2 members in it. The 2 members are this guy and that guy. Yeah, and then, this is kind of insane. Then we union that, right? Because unioning is the process of dumping out all the candy inside all the bags inside your big bag, right? And so when I apply union to, can I just write 6 to mean the set from the previous line? Then what do I get? I get all the things that are inside the things that are inside this blue thing. In other words, I get the empty set, the set containing the empty set, and the set containing the set containing the empty set. All right. Who is basically with me? That was bullet point. Oh no, we're not even done yet. That was bullet point 3. Can we just move on? I feel like we get the bigger point has been met. that this is via a process of sort of, it's a little bit of a subtle, a technical process of unordered pairing and unioning and unordered pairing and unioning, like every possible like combination is like a cheat code. Okay, this was meant to be, can we, given, suppose I have, this is now more generally, suppose I have sets x, y, and z, how do I in general make the set containing x? Yeah, you apply unordered pair to x, and you get the set containing x, x, and then that's just the set containing x. So we've seen that already. How do I get the set containing x, y, and z? It's kind of tricky, right?
Do that for all the letters, and then
You unordered pair, and then you union, and then you unordered pair.
Yeah, it's right. It's like I have. I guess I apply. I got to do it one at a time. I have to wrap all three, right? Yeah. So I apply unordered pair. I apply unordered pair to y, y, and that gives me the set containing y, y, which gives me the set containing y. Then I also apply unordered pair to z, z. I think all this is needed, and that gives me. And then that gives me z, z, which gives me the set containing z. Then I take, for example, then I apply unordered pair to x and y, which gives me the set containing x and the set containing y. I think I'm doing this right.
I don't think you need. You can just union x and y, or you can just unordered pair x and y together.
Isn't that what I want to do?
No, but like
No.
without the sets.
Oh yeah, maybe he's right. Do you think I could have done this in fewer steps? Okay, yeah, I only need to do it one. I only need one of these I need to do?
Yes.
Yeah. He's right. Okay, yeah. Instead I can just apply unordered pair to y and z. And then that gives me just like y, z. Yeah. Then,
those two.
yeah, then I apply unordered pair to the following two sets. Sorry about that. I kind of thought that was wrong what I had been doing. And that gives me the set containing x and the set containing y, z. Follow everyone?
Follow.
And then I apply union to that. And when I apply union to that, I get x, y, and z. Okay, and all right, good. So this new technical use of union is the one that makes its way sort of into the actual axioms. But you can also define regular union in terms of you can also define what we would have previously called just like regular union. How do I take the union of just two arbitrary sets A and B? Convince me that if I have a set A and a set B, I can make the set A union B.
Unordered pair and then union.
You unordered pair both of them with themselves? No.
No, just together.
Just pair them together.
And then you union it. Yep, he's actually right. Yep. You just create the unordered, you just apply the unordered pairs axiom to A and B. What does that yield? It yields the set containing A and B. Then what do I do with that set?
Union.
You union it. Yeah, and then when you take the union of this is just A, I'll just call that like old union. Like the old binary concept of union. All the things in A and B, that's what this union thing does. Okay, do you see how this like unary union operation is like more general somehow than the binary one? Okay, cool. This is like the basics. Are we all good?
Yeah.
Okay, good. These are like Lydia's long, tedious proofs of these that I don't think we need to go over because we kind of just did already. But if you want to look at this presentation later. Woo. Okay, so what we're starting to recover, this is starting to look a little bit like traditional set theory. Can you turn the camera? This is starting to look a lot like traditional set theory. Now that we have recovered the union operation, that's what's, no, that's a me.
To the board.
We've recovered. I mean, I am beautiful, but we have recovered the kind of in the way a little bit. We've recovered the traditional union operation. This is like traditional union. I've just convinced you, hopefully, that the traditional union operation is constructible in ZFC. What about the? What's wrong? What about the? Oh my God!
Y'all are fine. No, that's
Professional quality video making going on here. What about the intersection? Brian, stop talking.
Okay, just a second.
Can you not do that? What about intersection? What about the traditional intersection of two sets? The set of all things which are in A and B. Convince me that I can construct in the ZFC. You see what's going on right now? I've come up with these axioms, or Zermelo and Frankel did, and I am now trying to convince you that these axioms are indeed powerful enough to do all the things that you want to do with sets. Well, one of the things we want to do with sets is take the intersection of two sets. How does intersection work in ZFC? Well, it's actually kind of interesting, right? You take the property of being a member of set B, and you apply that to set A. This is our first use of the subset construction. Does everyone see what's going on here? I'm taking, the intersection of A and B can be thought of as the subset of A, which has the property that it's a member of B. Okay? And being a member of B is exactly the kind of thing that's like one of our properties. And then difference is basically kind of similar, right? I think this is a typo. No, there it is. I think this should say, oh, she just changed the definition of what this predicate means, right?
Why did you do that?
I don't know. She's now defining the predicate B to mean X is not in B. And so no. Okay. And we can also define the subset relation in terms of inclusion. I mentioned to you guys at the beginning yesterday that there's only one undefined relation in this entire ZFC. That is membership. And maybe you've probably seen this before, but in case this is your first time ever, well, it can't be your first time ever seeing this, but the subset relation is just definable in terms of basic logic and set membership. Okay, and so the entire sort of world of like basic 19th century set theory comes creeping back in. We have all these laws about union, that union and intersection are like associative, and all these extremely boring proofs that you might do for like a half an hour in discrete, and then like probably a half an hour again in many future math classes. Very boring, but very sort of important. It's just kind of, you just sort of Fitch-style proof it out. All of these facts about sets can all be proven from these ZFC axioms. Do you believe me?
Yeah.
Okay, good. Lydia wants to do one of the proofs. No time for that. Oh, here we go. This is important. I mentioned this. It's possible I've never mentioned this the entire year so far. I have at least said that it was true, but I don't think I've explained to you how it works. That ordered pairs themselves, you probably think, as a normal person would, of an ordered pair as like a primitive object, like just an ordered pair. And if someone asks you what's an ordered pair, you'd be like, dude, it's an ordered pair. Like, what do you mean? That's what ordered pairs are. Everything is a set in this new way of doing things. Can we define an ordered pair as a set? Yeah, we can. Does everyone see how technically this suffices, right? I'll define the ordered pair x comma y as a set of the set containing xy and the set containing x. And get it? You can then tell which is the left member of the ordered pair by which is the one that's in a singleton set and which one isn't. Who's with me? The asymmetry provides the like order. Yes?
No, I get it.
Cool. Woo, good. And then ordered triples can be defined recursively as like ordered pairs of ordered pairs. We good? A new axiom. We also want to take power sets often. So let's give ourselves this power to take the power set. What is the power set axiom? It's exactly what you think. It says, for any set, the power set exists. And what is the power set? It's the set whose members are all subsets of X. And so, given any set whatsoever, there's a new set Y, the power set. And what does it mean to be the power set? Well, I'll tell you what it takes to be a member of the power set. You're a member of the power set if you're a subset of X. So that's exactly what you would expect. Cool? Cool. Okay. So, this is just an example in case you forgot what a power set was. If A is like some set xy, then the power set of A is like the set of all subsets. And the empty set is always an element of the power set, so is the set itself an element of the power set, because every set's a subset of itself. If it's a finite set, then the power set has 2 to the n elements, etc., etc. Okay, notice that even with this power set axiom, we still only have the power to construct finite sets, right? I think that's probably what the next slide says. Because all we can really do is do the empty set and like union it together with other versions of the empty set. Okay, now this is going to get really technical. Okay, a couple of you are going to understand this and some maybe not. We need to make functions. That's certainly an important part of mathematics. Well, what are functions? They're just relations that satisfy other properties as well. What's a relation? It's a subset of the Cartesian product of 2 sets. So just imagine I want to construct a function from A to B. If I want, is that what I'm doing? Yeah. If I want to construct a function from A to B, then it's going to be, that function is going to be some subset of the Cartesian product, right? So the Cartesian product is this right here. It's the set of all ordered pairs. So far, so good. Except for the fact that these ordered pairs are not really ordered pairs, they're really sets. So every one of these ordered pairs is like 1 comma x is really the set containing 1 and the set containing 1 comma x. And so a set of ordered pairs is really like a set of sets of sets. Do you at least believe it? Okay, good. So how do I make a function from A to B? Well, if I want to make a function from A to B, I need to go like way deep into this. Okay, so first we take A union B. Think of this as all the elements of the domain and all the elements of the codomain. Throw them all together into one big soup. Then take the power set of that. Okay, the power set of that is going to be very, very big. And then we're going to take. Then we take the power set of that. Okay, the first time I tried to learn this, I just was stuck for like an hour reading this over and over and over again, trying to get my head around why the hell we would ever want to do this. And the reason goes back to this very technical definition of ordered pair, which is that these things are really sets of sets of sets. And so in order to be able to construct A cross B, I need to first take the power set of A union B, which is very, very big. It's going to have 2 to the 16th elements. And then we're going to extract from that only the very, very few ones which meet the condition. So, okay, this is just kind of super weird and maybe not the most important thing, but notice that A cross B, be with me that at least A cross B is a mathematical object that I certainly need the power to construct in ZFC, that's for sure. What is A cross B? It's just a simple set with 4 elements. But those 4 elements, having this deep structure that they have, we can only get by first going all the way up to this set of size 2 to the 16, and then extracting the 4 elements from that set that are actually relevant. And I think Lydia did like a pretty good job of this. Yeah, so she says, this A union B, the power set of A union B is going to be all the sets which, what's going on? Oh, all the sets, oh yeah. So the power set of A union B is going to be all the subsets of A union B, of course. But the only ones that are ever going to get used, because remember, she's continuing to remind us what A cross B actually is. Well, what are the pieces that I need to build in order to build A cross B? Well, I need the set containing 1x, and I need the set containing the set containing 1. So her purple.
No, just the set containing.
Just the set containing 1. And then I need sets of those. So notice how she's highlighted in purple the only elements of the power set of A union B that I'm ever going to possibly want, right? Because only these 6 purple things could possibly ever play a role in A cross B or A times B. And then when you take the power set of that, it turns out that only these 4 purple ones, these 4 purple things are the 4 things that actually end up making up A times B. But each of these 4 purple ones that I'm highlighting right now with my laser pointer, each of these 4 are in fact elements of the power set of the power set at A unit B. Do you guys have at least a vague idea about why you have to go up a whole nother level? Terrible lesson. All right, let's keep going. This is what I was starting to say like 5 or 10 minutes ago. What kind of current power do we have with just these 6 axioms? We can make finite sets. However, if you believe in actual infinity, which these kinds of people like Zermelo definitely believe in actual infinity, they are going to want to construct more advanced sets. For example, omega. The big idea here is we need to construct omega, which is in fact an infinite set, a set of infinite size. Do you feel that, do you agree with me that these axioms so far are not powerful enough to construct any infinite sets, right? They operate sort of discretely by making sets bigger and bigger. Even the power set axiom, sure, you can grow by a power of 2 every time you apply the power set axiom, but you're never going to get an infinite set. Agree? Woo! Let's go. Oh wait, no, not yet. First, this is a follow-up on what we reviewed yesterday. Let's define, you've already seen that the successor function can be defined in terms of set operations. So having done that, we are now, what we want to be able to do is to construct the naturals. So this is the what's it called, the von Neumann construction. Can we actually execute the von Neumann construction? Not quite. We can construct the empty set, of course. We have an axiom for that. We can construct 1 because it's just the successor of 0, which is just 0 union. We did this exact thing yesterday, right? And we get that. We can construct 2. We can construct 3, etc. So we can construct any finite number of natural numbers. But I don't want just finite sets of natural numbers. I want all the natural numbers together. So the goal is to somehow construct omega, this infinite set with all the naturals in it, because we think that the natural numbers are the kinds of math that we want our ZFC axioms to be able to build. Okay, so we're going to need some more. We're going to need to bring in some more heavy machinery. Do you guys appreciate this? Okay, so let's do it. A new axiom. This is the kind of thing that Bertrand Russell got in trouble for. Because he was trying to prove that all math comes from just logic, and one of his axioms he just had to come up with eventually was like, they are infinitely big things. And people protested, I think rightly, that is not an axiom of logic. Bertrand Russell, that's certainly a mathematical axiom. Well, ZFC doesn't have this kind of philosophical restraint associated with it. They can just simply assert axiom of infinity. This axiom is a little bit subtle. What does it say? Well, I'll do it in English first. It says, define a set as inductive if the set contains 0, and whenever it has a number, it has that number's successor. Okay? Where successor was defined as on the previous slide. And so, what can I say about this set? Well, it certainly contains all the natural numbers because it has 0 in it. Whenever it has a number, it has its successor. So it is some kind of omega or omega plus monsters. Okay, and let's look at now the technical first order logic. This axiom of infinity just asserts the existence of a subset A with the following property. Well, the empty set's in A, and whenever something is in A, the successor is in A. Okay, then a very technical proof that's like slightly over my head, maybe right on my head. I've read it before, but it's really hard. We're not going to do it. That you can prove that of this axiom tells you merely that there exists a set which is omega plus possibly more things. You can prove that of all these sets, there is a smallest one. And hence, we can define omega within this system to be the sort of, you can think of it as the intersection of all of these sets A, or the smallest of all the sets that meet this axiom. Okay, so you're taking this on faith a little bit because I'm skipping all the details. We now have the power, with these axioms 1 through 7, of creating, depending on philosophically how you want to phrase it, we have in some sense created the natural numbers. Or a more skeptical summarization would be, we have constructed within ZFC, using the machinery of set theory, we have constructed essentially a model of the natural numbers. If you're very bold, you might think that this is actually what the natural numbers are. But if you're less bold, we've at least simulated the natural numbers using sets. Now, this had already been done prior to ZFC. And this was one of the big important things that set theory was good for. Building the natural numbers and doing arithmetic in sets. And what we have just demonstrated with a lot of hand waving is that these specific set of axioms are powerful enough to carry out this program. And we really just now have these objects which basically act like the natural numbers. They satisfy the Peano axioms. Yo.
Is the seventh axiom necessary in Peano arithmetic? Because I don't remember doing much with like omega with Peano arithmetic.
Peano arithmetic, well, we're actually about to review the axioms of Peano arithmetic now, right? So what are the axioms of Peano arithmetic? There were like 4 or 5 of them, right? Essentially, they that zero was a number, right? So here we get that automatically because 0 is just defined to be the empty set, and the empty set is a member of omega because of how we made omega in the previous slide. Another axiom of Peano arithmetic was for every number, the successor is also a number. Well, once again, we built that into the definition of being an inductive set, that whenever a number is in there, so is the successor. So, so this set omega does have this property. What was the other axiom? The other axiom was that no one has a successor of 0. Well, once again, technically we can prove this, right? Because suppose that there was some number x such that its successor was 0. Well, the only way for that to be true, the successor is defined as x union set containing x is 0. But 0 is just the empty set. So how could x union the set containing x be the empty set? Because x union the set containing x has at least one element in it, x, right? X is an element of x union the set containing x. And so that's just impossible, right? X is in the is always an element of the successor. Okay, so haven't exactly answered your question yet, but maybe your question is no longer relevant. Do you see what's going on? Omega just is the set that the Peano axioms are applying to. And so I've made in ZFC like the overall thing, and now I'm going to point to that thing omega and say you satisfy the Peano axiom. And it doesn't stop there. Of course, the other one is what is this? Oh, this is induction. Of course, the other big axiom of Peano arithmetic is induction. We need to prove that whenever 0 is in some subset of omega, and whenever something is in that subset Q, given any subset of omega, if 0 is in that subset, and if whenever a number is in the subset, the successor is in that subset, then we want to claim that subset is in fact all the naturals. Right? That's a slightly different way of stating induction, but you guys recognize that as just a variant of the principle of mathematical induction, right? This is if you have that in fact to show that, yeah. You can think of Q, yeah. All right, good. Woo! So how do you do this? You just start, man. You start with some subset Q, and you suppose that the empty set is in it, and that whenever a number is in it, the